Hello everyone, my name's Dr. Peter Green and welcome to this first tutorial on sequential Monte Carlo samplers, which has been created for the Centre for Doctoral Training in Distributed Algorithms, which is hosted here at the University of Liverpool. So just to give you a bit of background, the Centre for Doctoral Training is an EPSRC funded initiative that's sponsored by for example, STFC Hartree, IBM, the Alan Turing Institute, and so on. And it is a cohort-based model for the training of PhD students, specifically focused on distributed algorithms. It's also associated with this EPSRC funded project, which is called Big Hypotheses, which is about developing Bayesian inference solutions which are suitable for modern computing architectures. And at the heart of this project is an algorithm that's called a Sequential Monte Carlo sampler. And obviously it's closely related to the Centre for Doctoral Training because it's about having an algorithm for Bayesian inference that can be distributed over large computing architectures. So this video is going to be the first in a series of tutorials about sequential Monte Carlo samplers. So this is going to be one of the more advanced sets of videos that I put onto this channel. But what we're going to do is start off relatively simple, and then through the videos eventually we'll build up to the outputs of one of our academic papers. So this should be the first set of videos on this channel that kind of leads to a YouTube explanation of a paper. But like I say, we're going to start relatively simple. So we'll start by discussing the context. Okay, so we'll have a look at the situations where you might consider applying a sequential Monte Carlo sampler, why you might need it, and we'll discuss where this approach fits with other approaches that are in the field. And then for the second part of this video, we'll look at importance sampling, which really lies at the heart of sequential Monte Carlo samplers. So that's what we're going to do in this video. So we're going to start by describing the basic fundamental problem that we want to address, and then we'll give some context to that problem with an example. So the fundamental problem is that we have some kind of probability distribution, which I'll write as pi of x, and what we want to do is to evaluate, or at least estimate, the expected value of some function f of x with respect to this probability distribution. So if f of x was just equal to x, then we'd be trying to evaluate or estimate the mean of this distribution, for example. And we're going to stick with continuous variables throughout this set of videos. So in that case, we know that this expected value is equal to the following integral. So it's the integral of the function we're interested in, f of x, multiplied by the probability distribution pi of x dx. And just to establish some semantics, we're going to refer to this thing throughout the videos as the target distribution. Okay. So one of the things we might do if this integral is difficult for whatever reason is we might decide that we want to try and get a Monte Carlo estimate. So what does this involve? Well, let's say somehow we have a way of generating samples from our target distribution. So we're going to generate n samples and we're going to give each one a superscript. So we have x1 is our first sample up to xn, so the superscript is used as an index for each sample. And we've managed to generate those from pi of x. Once we have those, we can realise an approximation for this expected value, i.e. an approximation for this integral, by saying that our expected value of fx is roughly equal to, then we have our Monte Carlo estimate is essentially the average of our samples evaluated at f. So it's going to be 1 over n multiplied by the summation of our samples each evaluated at f, where if my notation's right, which honestly sometimes it's not, but from what I remember, this represents asymptotically equal to. So in other words, as n goes to infinity, then this approximation will tend towards the true value of this integral. Okay, that's fine. But then the next question might be, well, how do we generate all of these samples? In other words, how do we generate this lot? So if pi of x, if this distribution is something standard, like a Gaussian or a Poisson or something like that, then there's set ways for generating samples from them. But if it's something that's non-standard, then you'll have to turn to something else. So probably the most well-known approach to generating samples from a generic probability distribution is Markov Chain Monte Carlo. Or otherwise known as MCMC. And when do we have to do this? So this is the basic problem that we've got. Is we've got this target distribution pi. We want to estimate something that's related to it. And so we're going to generate samples for that purpose. When does this come up? Well, most of the time it comes up when we're doing something Bayesian, something that involves writing down Bayes' theorem. So I've got some videos about Bayes' theorem as well that might be of interest. But usually, let's say our target distribution is actually given by Bayes' theorem. So what we're interested in is probability of x given y, which we've decided to address by writing down Bayes' theorem, like I've shown here. And to give context, perhaps this is some data from an experiment, for example, and x is some model parameters. So in other words, we're fitting a model to some kind of experimental data. We're doing it by essentially tweaking the model's parameters. And what we want to do is get a probability distribution over those parameters given the data that we've obtained. So some of the time you can use Bayes' theorem to get a closed form solution for the posterior probability distribution. So this will come out as something standard, let's say. But that's usually only because we've been quite careful about how we choose the likelihood and the prior. And in fact, most of the time, if you have a nonlinear model, for example, Bayes' theorem will actually give you a non-standard distribution. But it's a distribution that you can evaluate at any point. So we can substitute a value of x into here, and we can evaluate Bayes' theorem at any point x. but it's still non-standard. So it's still going to be, let's say, difficult to generate samples from. And so that's why we might need something like Markov Chain Monte Carlo. So what we're going to do, rather than look at MCMC, is we're going to look initially at an alternative, like I said, called importance sampling. So we're going to introduce a new distribution called Q, and we're going to call this the proposal distribution throughout. And all we're going to do is say that Q is easy to sample from, okay? So unlike pi, it's our target distribution, we're going to say that Q is some kind of standard distribution like a Gaussian. And then we're going to take the integral that we want to approximate. So remember, that's the integral of f of x multiplied by pi of x. And we're going to take the term inside the integral. We're going to both multiply and divide by q of x. So this becomes the integral of f of x pi x over q. So target over proposal, and then there's our proposal there as well. So we've not changed anything in its integral. Obviously, these cancel. And then what we're going to do is we're going to write this term now as w, where w is the ratio of the target distribution to the proposal, and is usually called an importance weight. Some slightly dodgy handwriting there. So, well, why did we bother doing this? Well, now let's write down our Monte Carlo estimate of this. Because now it looks like, rather than, if you remember before, we're going to estimate f of x by generating samples from pi of x. Now we can think of it as saying we're going to try and estimate f multiplied by w using samples that are generated from q. So specifically, that means we are going to approximate this as our 1 over n, and then our summation. And like I say, we've got our function evaluated at the ith sample, multiplied by this importance weight at the ith sample, where now each of our samples, so xi, I should say x1 to xn, so they've now been generated from q. So this should get us around the problem, because now all we've got to do is we generate samples from Q, which we've deliberately chosen to be something that we can sample from easily. And for each sample, we evaluate F multiplied by W, where W is this ratio of target to proposal. And then we add them all up and divide by N, and then we've got our Monte Carlo estimate. So one way that you might want to think about this is we're generating samples from the wrong distribution because it's not pi, but these weights correct for that error, if you like. So that's one of the kind of interpretations that you can use for importance sampling. Now, as I'm sure you could probably work out, it helps if Q is similar to pi. So if we have a one-dimensional example, so let's say this is X, and we've got our target distribution is something a bit weird, yeah. So that is pi. Then it helps if our proposal, so let's say it's Gaussian, so it's easy to sample from. It helps if the proposal is something similar. So in the ideal case, your proposal would actually be completely equal to the target. So if Q is equal to pi, then this would cancel, this would be unity, and this would become pi, so you'd be left with the original integral. As what we've done here is we've been lucky and we happen to have suggested a proposal that has roughly the same support as the target. If we made a mistake, and let's say let's go back to here. Let's say we actually accidentally used a really, really enormous proposal distribution. So that's our new Q of X. Then what could happen is that our Monte Carlo estimate is dominated by very few samples. So let's say we generate some samples from Q and they land here. Yeah, that'll do. Then for these samples, you'll have the situation where pi of X is pretty much equal to 0. And so the weights associated with these samples will be essentially 0. And so they won't appear significantly in this summation. And in fact, the only sample that's landed in a good region, let's say, so a high probability density region of the target, is this one. So this is the only one that will have a significant importance weight. So actually, even though we've generated, okay, in this case, just 5 samples, it means that the Monte Carlo approximation in reality will only really be using one of them. So the variance of this estimate could be very large, okay, and you could get a very inaccurate estimate of this integral. Likewise, you can imagine, let's say, rather than this large proposal, it should be fairly obvious that you can also make the other mistake and have a proposal that's really narrow. Okay, this doesn't look very Gaussian, but I think you can see the point. And if you have a proposal that's too narrow, its support is too narrow, then in this case it'd be at least very improbable that you can get samples across all of the important regions of the target distribution. So intuitively, it should be obvious that the choice of proposal is going to have a dramatic effect on the efficiency of your algorithm, i.e. the number of samples that you need to realize an accurate approximation of this integral using this Monte Carlo approach. So I think that's far enough for this first video. So to summarize, we've got some kind of target distribution where we want to estimate this quantity, f of x, or its expected value. One of the ways we can do that is by generating samples from the target, realizing a Monte Carlo estimate. However, if, for example, you're using Bayes' theorem, and Bayes' theorem is the target distribution, then you might end up with a non-standard probability distribution, in which case, to generate samples from it, you might need an approach like MCMC. An alternative to MCMC is importance sampling, which we've discussed here. So now in the next video, we'll talk about what problems you might have if you try and use importance sampling, and therefore motivate why we need sequential Monte Carlo samplers.